This recording is going to cover the events that take place in the Loop of Henle. Now, the Loop of Henle is actually composed up of three components. You have the descending limb of the Loop of Henle, because the fluid in there is moving from cortex down into the medulla. Now, that is thin-walled. One thing is that descending limb is freely permeable to water. It's very highly permeable water because it has a presence of an aquaporin channel called aquaporin 1 in the wall. But there is no movement of solutes. There are no transport proteins for it there. Hence, the descending limb is very thin-walled. It's squamous cells. Doesn't need to be any bigger because we don't really need any transport proteins in there. We don't have any. So freely permeable to water, but impermeable to solutes. The ascending limb has two components. And again, we call it ascending limb because now we're moving from medulla back up to the renal cortex. The thin ascending limb does involve some little passive transport of sodium chloride. Not a lot going on there. The thick ascending limb is more important for you to understand than the thin ascending limb. This one involves active transport of ions, but it is impermeable to water because of the lack of the aquaporin channels. The sodium and chloride and potassium are actively transported into the medullary space in the thick ascending limb of the Loop of Henle. Now, I'm going to do first, I'm going to come back to this here, is I want to kind of just talk about the mechanism by which we actively transport the sodium and chloride and potassium. Is we have a co-transporter in that luminal membrane, and it's called the 1 sodium, 1 potassium, 2 chloride co-transporter. So it is a co-transporter. It's what we call a symporter because these things are moved in the same direction, and these ions are actually transported actively. It's actually an example of secondary active transport because over here that sodium-potassium pump in the basolateral membrane is actively pumping sodium out of the cell, which creates a favorable gradient for sodium over on this side to enter the cell. And so we're able to actively transport various ions into the medullary space, which you see here, peritubular fluid. So it's actually the interstitial fluid in the renal medulla. Now, in the thick ascending limb of the Loop of Henle, you also have transport of other ions, such as calcium, but the calcium is actually transported through the paracellular route. It's not actively transported, so it's going between the cells. But I want to go back and talk about the Loop of Henle and the reason for these differences in the permeability of the segments to water and solutes, because it's going to be extremely important. So if I come back, actually we can just use this picture, is the descending limb we said was permeable to water but impermeable to solutes. Okay, again because of the presence of aquaporin 1 in its tubular wall. So as water moves across the tubular wall into the medullary space, the filtrate, you'll notice, is becoming hypertonic. It's becoming more concentrated. Now, if you look at the thick ascending limb, which is impermeable to water because it lacks the aquaporin channels, but it's actively transporting sodium and chloride and potassium into the medullary space. If you look at the tubular fluid contents, the filtrate is becoming hypotonic. It's being diluted. The interstitium, though, well, you'll notice the interstitium is steadily getting more salty or hypertonic, and it will attract water when we talk about later if over here that's going to be permeable to water. That's going to be important. Now, the countercurrent flow in which the descending and ascending limb is arranged so they're countercurrent to each other. This is going this way, this is going this way. That countercurrent fashion in which the flow is taking place is actually going to increase or multiply the osmotic gradient between the tubular fluid and the interstitial space. And the arrangement, how the loop of Henle is responsible something for we call the countercurrent multiplication or countercurrent mechanism by which urine it can be concentrated in the nephron. Now, countercurrent mechanism or countercurrent multiplication is a mechanism by which energy is expended to create a concentration gradient. And a functioning loop of Henle is responsible for creating a concentration gradient within the renal medulla, which you see here. It goes from 300, here 600, 900, and down at the very tips, you've got a concentration of 1,200 milliosmoles per liter. But the kind of things that are involved, we're going to go through these steps. There's these steps that are involved in creating this osmotic gradient. So the thick ascending limb, you'll notice that thick ascending limb has that sodium potassium 2-chloride cotransporter. Now, I didn't mention previously is that, I'll go back to that picture, is the reason why it's 2 chlorides is you got 2 positive charge ions coming in. You need to counteract that 2 positives with 2 negatives. Otherwise, you can change that membrane potential. That's why it ends up being 2 chloride. Now, let's come back here again. So we have that cotransporter in the ascending limb that helps to create a gradient by pumping sodium into the medullary interstitium. That the thick ascending limb is the only part of the nephron tubule that lacks aquaporins, so it's impermeable to water. So the action of that transporter creates a hyperosmolar solution in the tubular fluid, and then a hyperosmolar fluid in the interstitium, since water can't follow the solutes. I should say I meant to say the tubular fluid is hypoosmolar, but the interstitium is hyperosmolar. It's more concentrated. Now, since the descending limb, a loop of Henle, has a very leaky epithelium, it's got a lot of aquaporins in there. The fluid inside that descending limb becomes more concentrated, so it's being drawn out here. Now, what happens is that movement, the movement of fluid through the tubules, and the way it's designed in this kind of countercurrent fashion, it causes these contents to move further down the loop, and with repeated cycles, what's going to happen is, actually I should say, is this is bringing the sodium and the chloride to this segment, which is then pumped out. And what happens is you have repeated cycles of what this is going on, is it causes the fluid near the top of the loop of Henle, up here, to be isoosmolar, 300 milliosmoles per liter, which is what you have in your blood, but that's very, very concentrated at the bottom of the loop of Henle, which is about 1,200 milliosmoles per liter. Now, having the long loops of Henle allows us to be able to have a concentrated urine, and it's really the loops of Henle in the juxtamedullary nephrons, which have very long loop of Henle, go deep into the medulla. Those are going to be important for if we want to create a concentrated urine. Now, the animals that have a very strong need for a concentrated urine, things that live in the desert, they have very long loops of Henle, so they can create a very large gradient, greater than ours. Ours, the maximum is about 1,200. Some animals, it's 10,000 milliosmoles per liter. Animals that have water, abundance of water around them, they have very short loops because they don't need to concentrate their urine as much. Now, the vasorecta, which are those blood vessels that are associated with the loop of Henle, they have a very similar loop fashion as they run countercurrent. They run countercurrent to themselves as well as to this loop. And having that set up is very important so we don't dissipate this gradient that we see here, because otherwise, if it was set up differently, the sodium that was in that interstitium would be taken away by the vasa recta, but it isn't because of the way the vasa recta are designed. So the mechanism of this countercurrent multiplication works with the countercurrent exchange that we have in the vasa recta, and that helps to prevent washout of salts that we have in that medullary interstitium, and maintains a very high osmolarity at the renal medulla. So the countercurrent mechanism is extremely important in our ability to create a concentrated urine under the right situation. So here would be the situation, is we have this dilute urine up here, but we've created this gradient in the interstitial space. Is when this fluid is moving down now towards the medulla through the medullary ducts, is if it's ADH is present, that it's going to have, you're going to insert a lot of aquaporin channels in that duct. Is what's going to happen is water is going to be drawn out, and as it's drawn out, the concentration of the tubular fluid will be the same as you find in the interstitium. So at this level will be 600, here it's going to be 900, here it's going to be 1200. That's a concentrated urine. Now, if ADH isn't present, we would have, water's not going to leave, but we're going to still actively transport ions through here, because the medullary duct can actively transport ions there. Is the fluid contents are going to be dilute. So they're going to get more and more dilute. So having a functioning loop of Henle is extremely important for us to be able to create a concentrated urine under the right conditions. If all parts of your nephron tubule were permeable to water, the osmolarity of the urine would always be the same, and you couldn't alter it. So it's extremely important. We do have different components of the nephron tubule with different permeabilities to water, and also technically salts too.